As per your syllabus, we are going to study the detailed chemistry of three heterocyclic compounds called pyrrole, furan, and thiophene. However, before we go for the details of these heterocyclic compounds, first of all, we must learn the method of nomenclature of heterocyclic compounds. Till now, in organic chemistry, you have come across various straight chain compounds, their derivatives, as well as you have seen fused ring structures like naphthalene, anthracene, etc. However, you have not read these heterocyclic compounds. So let us see how the nomenclature of these heterocyclic compounds are done. When we talk about the nomenclature of heterocyclic compounds, there are three systems in general used for naming heterocyclic compounds. The first method is the common method of nomenclature. Sorry. As per this method, either little or no structural information is obtained regarding the structure. However, it is still used quite widely. Okay. So we can say this common nomenclature, it gives us idea regarding the trivial name, or what to say, the common name in general. Okay. It has got nothing to do with its detailed structural information. The next method is the most method is replacement method. Okay, we will see the details of the methods in the coming slides. When it comes to common nomenclature, the first method of nomenclature, each compound the heterocyclic ring. For example, if there is more than one heteroatom of the same time are there in a compound, say for example, this nitrogen or this nitrogen. However, which one should be given? repeat, and we can move forward with the numbering in such a way that the second heteroatom should get the minimum numbering. Now, if there is more than one type of heteroatoms, in that case, the ring is numbered starting at the heteroatom of higher priority. Okay. Now, what are the commonly observed heteroatoms in heterocyclic molecules? The most common heteroatoms that are observed in case of heterocyclic compounds are oxygen, sulfur, nitrogen. Only at very rare times we can come across phosphorus or selenium. However, in general, the heterocyclic compounds bear heteroatom as oxygen, sulfur, and nitrogen. And if we compare the priority, then oxygen has got higher priority, or oxygen is given higher priority as compared to sulfur, and sulfur is given higher priority as compared to nitrogen. Okay. And it continues in the direction to give the other heteroatom the lower possible number. Okay. Suppose we have got more than one heteroatom in a heterocyclic ring. Of course, as per priority, we have to give the first high or higher priority bearing heteroatom is supposed to get the position number 1. However, when we move forward, we should do the numbering in such a way that the other heteroatom which is present in the ring should get the minimum possible number. If substituents present or substituents are attached to the heterocyclic ring, then their position should be identified by the number of the atom bearing them, and then they should be listed in their alphabetical order. So, while doing the nomenclature of heterocyclic compound, first what we have to do, based on their priority or based on the priority of the ring heteroatom or the heteroatom present in the ring, first we have to do the numbering of the ring. Then we have to see which position or which to which position or which number the functional group or atom is attached. Here we can see to the 4th position Br substitution is attached, and to this 5th position we can see the amino functional group is attached. After seeing this, we have to organize them, or we have to list them in their alphabetical order. The words dihydro or trihydro or tetrahydro are used if 2 or 3 or 4 atoms are saturated. Now sometimes we can see that the ring is associated with unsaturated bonds, that is double bonds. Likewise, at times we can see structure or heterocyclic rings where some points or some bonds are saturated. Some sides of the heterocyclic ring is saturated. Depending on the number of sides where saturation is there, if there are, or if a single bond or at one double bond saturation has taken place, in that case 2 hydrogens are added. If 2 bonds are saturated, then tetrahydro we have to say. And depending on how many hydrogens atoms are attached to the heterocyclic ring, to get the saturated or partially saturated structure, we have to name it accordingly. These words, this dihydro, trihydro, tetrahydro, these words are preceded by numbers indicating the position of saturated atoms. Now, if we see this structure, here we can see the heterocyclic ring is a 6-membered ring called pyridine. Okay. Of this heterocyclic ring, if we do the numbering, then we would number it like position number 1, 2, 3, 4, 5, and 6. Now, here the double bond between the first position and the second position is saturated. So, 2 hydrogens are attached. One hydrogen atom is attached to the position number 1, that is nitrogen atom, and second hydrogen is attached here to the carbon atom. Hence, the name of this heterocyclic ring will be 1,2 dash dihydropyridine or 1,2 dash dihydropyridine. So here we can observe there are 2 hydrogen atoms attached to saturate this bond. And where is this saturated bond located? Between the position number 1 and 2. Is that clear? There are several heterocyclic rings included in our syllabus. Now let us see the trivial names given to some of these rings. When we talk about 5-membered heterocyclic rings with 1 or 2 heteroatom, the most common heterocyclic rings are shown here. For this heterocyclic ring, to be specific, 5-membered heterocyclic ring with 1 oxygen in the ring as heteroatom, this heterocycle is called as furan. If oxygen is replaced with sulfur, then we call the heterocycle as thiophene. Now, when the 5-membered heterocyclic ring bears nitrogen or only 1 nitrogen atom as heterocycle, as a member of this heterocyclic ring, then the structure is called as pyrrole. Okay. Furan, thiophene, pyrrole. Likewise, 5-membered ring with 2 nitrogen atoms or 2 nitrogen atoms as heteroatoms in the 5-membered heterocyclic ring is called as imidazole. Similarly, if the relative position of these 2 nitrogen is, instead of being 1, 3, it is 1, 2 position, then this heterocyclic ring is called as pyrazole. Most of the times, students, they get confused between these 2 names. 1, 3 relative position is called as imidazole, whereas 1, 2 relative position is called as pyrazole. Similarly, if oxygen as well as nitrogen both are present in the heterocyclic ring, then we call it as isoxazole if their relative position is 1, 2. Similarly, if their relative position is 1 and 3, in that case, we will call it as oxazole. 1, 2 relative position, isoxazole. 1, 3 relative position is called as oxazole. If sulfur and nitrogen both are present in the 5-membered heterocyclic ring and their relative position is 1, 3, in that case, the common name given to the heterocyclic ring is thiazole. So, the common 5-membered heterocyclic ring includes furan, thiophene, pyrrole, imidazole, pyrazole, isoxazole, oxazole, and thiazole. Now let us see the 6-membered heterocyclic rings with one or two heteroatoms. When a six-membered heterocyclic ring bears one heteroatom oxygen in the cycle, then it is called as pyran, to be specific, 2H pyran. Here, the position number 2 or the carbon which is present at position number 2 is saturated, hence only 2H pyran. Here, if we observe the structure, here we can see the carbon at position number 4. If we start the numbering with the heteroatom oxygen as position number 1, then this carbon 1, 2, 3, 4. This carbon acquires position number 4. Fourth position is also saturated here. So here we can name this, or we can call this heterocyclic ring as 4H pyran. Okay. Now the common azenes, which are six-membered and aromatic, in addition nitrogen containing heterocycles, then we will come across these four members or these four heterocyclic members. The first and the simplest member of this category is pyridine. Here we can see a six-membered unsaturated ring with nitrogen, only one nitrogen present in the ring as heteroatom. If there are two nitrogen atoms present in the six-membered heterocyclic ring at relative position of 1, 2, we will call it as pyridazine. Similarly, if the relative position is 1, 3, then we will call it as pyrimidine. You must have come across this term when you studied the various structures of DNA or RNA bases. Purine and pyrimidine bases. Do you remember? The next category of heterocyclic six-membered ring, where there are two nitrogens present at relative position of 1 and 4, then we call this structure as pyrazine. Let us have a recap of these four heterocyclic rings. First, pyridine. Second, pyridazine. Third, pyrimidine. And fourth is pyrazine. Now let us see the trivial names given to the fused heterocycles. When we talk about fused heterocycles, we talk about cyclic compounds or compounds where two cyclic structures are fused with each other. Either both of them may be heterocyclic or one may be heterocyclic. It depends. Okay. So the most commonly observed fused heterocyclic structures include, first is indole. Here we can say one is a benzene ring. Benzene ring is fused with this pyrrole, isn't it? So we get a structure called indole. Here, the site of fusion has been changed and the structure is called isoindole. Similarly, we can see structures called as imidazole, purine. Likewise, indolizidine, and here a purine base or guanine. Okay. Here we have taken the example. This is the purine derivative or purine ring, and purine ring is associated with its substitutions to give us this guanine base. The common ring fused azenes or common rings bearing fused azenes include quinoline, isoquinoline, quinazoline, pteridine, quinolizidine, of which these two, quinoline and isoquinoline, is included in your syllabus, which we will study in detail as we move forward. Some other trivial names include coumarin, chromanforone, flavone, carbazole, dihydroacridine, etc. Now let us see some saturated heterocyclic compounds and their trivial names. Here if you see the structures, there is no double bond inside these cyclic structures. It indicates that all the structures are saturated in nature. Hence we call them as saturated. However, as because they are cyclic compounds, we call it as cycles. And as because they bear a heteroatom in the cyclic structure, we call it as heterocycles. So in all, we can call it as saturated heterocycles. The first example under this category I have taken here is pyrrolidine. Next is piperidine. Here, two heterocyclic compounds and both are saturated. Piperazine. And here we can see two different heteroatoms, nitrogen and oxygen, present in the name, in the saturated heterocyclic name, and the relative position is 1,4. The structure is called as, or the trivial name of the structure is morpholine. Okay. Now, based on this, I wish you can find out the name of these structures. The second method is the replacement method of nomenclature. Till now, we saw the trivial nomenclature. Next, we will see the replacement nomenclature. And in the final place, we will see the IUPAC nomenclature. Okay. So in replacement nomenclature, what happens? The heterocycle's name is composed of the corresponding carbocycle's name and an elemental prefix for the heteroatom is introduced. Okay, if more than one heteroatom is present in the structure, then that will be listed according to the priority given as shown in the table below. And according to this nomenclature, tetrahydrofuran is called as, when we talk about tetrahydrofuran, we are talking about a 5-membered heterocyclic ring with one oxygen atom. Okay, and when we are talking about tetrahydro, there are 4 hydrogens attached to this furan ring. Okay. Now, in replacement method, this tetrahydrofuran is called as oxacyclopentane. If you see the structure, oxa stands for oxygen atom. Cyclo means it is a cyclic structure. Then the name pentane. It means it is a 5-membered structure, and the term ANE indicates that it is a saturated heterocyclic compound. Now, what are the commonly used heteroatoms? Oxygen, sulfur, nitrogen, and at times we come across phosphorus and selenium. If oxygen atom is present in the heterocycle, then the prefix oxa is attached. For selenium, selena. For sulfur, the prefix used is aya. Likewise, for nitrogen, the prefix used is aza, and for phosphorus, the prefix used is phosphor. Okay, and here we can see the priority. Okay, oxygen, higher priority bearing atom, next sulfur, next nitrogen. As per this replacement method of nomenclature, we can see the nomenclature of some of the compounds here. See, this is the structure of benzene. Okay. Here we can see this benzene ring has been attached with two heteroatoms. What are these two heteroatoms? Two nitrogen atoms. Where they are attached? They are attached at position number 1 and 4. Hence, we will call it as 1,4-dia or diaza. Di for 2. Aza means nitrogen. Where they are attached? They are attached to the benzene ring. Hence the name 1,4-diaza benzene. Likewise, if it is the structure of cyclopentadiene, then this structure will be called as oxacyclo 5 members are there in the ring, hence penta, and 2,4-diene. The next example of this category is this heterocycle. It is also based on the basic ring called cyclopentadiene. Here we can see two heteroatoms, oxygen and nitrogen, are attached to the ring. Hence we can call it as 1-oxa. If we see the priority list, oxygen is given higher priority as compared to nitrogen. Hence the numbering will start from oxygen. Okay. Now the numbering should move in this way, 1, 2, 3, because in this way nitrogen gets the next minimum possible number. The replacement method. In replacement method, this compound can be called as 1-oxa, 3-aza, cyclopenta, 2,4-diene. Similarly, the structure will be called as oxacyclo. It is a 3-member saturated ring. Hence, cyclopropane. Here, oxa and aza. Two heteroatoms are attached. Oxa, aza, cyclopropene. Here, same cyclopentadiene based ring structure with two heteroatoms, sulfur and nitrogen. Priority wise, sulfur is given higher priority as compared to nitrogen. Hence, position number 1 is given to thia or sulfur. The name of the structure is 1-thia, 2-aza, cyclopenta, 2,4-diene. Likewise, this structure, which is based on the structure of cyclohexane, is called as 1-oxa, 4-aza. The structure is cyclohexane. Hence 1-oxa, 4-aza, cyclohexane. This is based on the structure of naphthalene. This is called as 2-aza because it is here we can see this nitrogen is attached to position number 2. We will start the numbering from here. Okay, so this carbon is given as a position number 1 and this nitrogen gets position number 2. And the name of this structure as per replacement method of nomenclature is 2-aza naphthalene. This is thiacyclohexane. This structure, if we see the numbering, it is naphthalene based structure. That is, the basic ring is like naphthalene. However, at the point of fusion, we can see a heteroatom nitrogen present in the ring structure. So the numbering is done just like this: 1, 2, 3, 4, and this site of fusion is always numbered as or as per the previous position number. This position comes after position number 4, hence it is called as 4A position. Okay, and this fourth position is a saturated one. Here there is no double bond. Here one hydrogen is attached. Hence we will call this structure as 4H. 4A azanaphthalene. Where is the aza atom placed in this naphthalene ring? It is placed at position 4A. In addition, the fourth position is saturated with the presence of one hydrogen. Similarly, here we can see two thia or two sulfur atoms attached to this naphthalene ring. The same naphthalene term will be there. However, two thia are present, hence dithia. Where they are present at position number 1 and 4 respectively. Hence, we will call it as 1,4-dithianaphthalene. The last method is the IUPAC method, or it is also called as Hans-Widman nomenclature method. As per this method was actually named after the German chemist Arthur Hans and Oscar Widman, who proposed similar methods for the systematic naming of heterocyclic compounds in the year 1887 and 1888 respectively. As per this system, 3 to 10 member rings are named by combining the appropriate prefix that denotes the type and position of the heteroatom present in the ring with suffix which determines both the ring size and the degree of unsaturation. So when we talk about this Hans-Widman nomenclature method, there will be prefix as well as suffix. What this prefix gives? The prefix denotes the type and position of the heteroatom present in the ring, whereas suffix tells us about the ring size and the degree of saturation or unsaturation. Now here we have to note that fully saturated and fully unsaturated rings have got certain rules for nomenclature, while partially unsaturated rings will be indicated in certain ways. So what are the ways that we will see in detail as we move forward? Apart from this, the suffix used in IUPAC nomenclature helps us to distinguish between nitrogen containing heterocycles and heterocycles that do not contain nitrogen. So in all, we can say the IUPAC nomenclature or Hans-Widman nomenclature has got 3 parts in its nomenclature pattern. First is locants, that is positions. Next is prefix, and third is suffix. Here we can see the position number. Here we can see what sort of ring it is. 5-membered ring, 6-membered ring, what type of heteroatom is attached, etc., etc. And suffix gives us the actual size of the ring and the degree of saturation and unsaturation. Okay. So there are 3 parts in all. First is the positions or locants. Second is the nature of heteroatom attached, and here we can get the ring size, idea about ring size and the degree of saturation, unsaturation, partial saturation, etc., etc. Now let us see this points or the method of IUPAC nomenclature in detail. When we see this Hans-Widman rules for fully saturated and fully unsaturated heterocyclic cycles, The first point to be taken care of is, first we have to identify the heteroatom present in the ring. Okay, and that should correspond to the prefix. For example, if at all sulfur is there, the prefix should be thia. If at all nitrogen heteroatom is present in the ring, the prefix is aza. If oxygen, then oxa. The position of a single heteroatom control the numbering in a monocyclic compound. If only one heteroatom is present, then the numbering is done in such a way that the heteroatom gets position number 1. Okay, if only one heteroatom is present in a monocyclic compound, here try to notice single heteroatom and monocyclic compound. The heteroatom is always assigned position number 1. And if substituents are present, they are taken or they are counted around the ring in such a manner that they get lowest possible number. So when we see the numbering of this, or when we do the numbering of this cycle, we will never number it like 1, 2, 3, 4, because at that time this ring substitution get very high position number, whereas numbering should be done in such a way that the substitution get minimum possible number. So we will move like this: 1, 2, 3, 4. Third point to be taken care of is a multiplicative prefix like di, tri, etc. In the earlier slides, we saw structures where a single heterocyclic structure bears more than one heteroatom. Sometimes this more than one heteroatom, they may be the same atom or they may be two different atoms. If they are same, then the term di, tri, etc. are used. And locants are used when two or more similar heteroatoms are contained in the ring. For example, we saw 1,3 relative position, 1,2 relative position. We saw the structure of isoxazole, oxazole, pyrazole, imidazole, etc. It's nothing. Now, in case of a multiplicative, or in case the ring structure bears more than one heteroatom of the same type, then a multiplicative prefix, that is di, tri, etc., and the locants are used when two or more similar heteroatoms are contained in the ring. If two nitrogen atoms are present, we will call it as diaza or diaza. Di means two, aza means nitrogen, two nitrogens, and the numbering preferably comments at a saturated heteroatom, then an unsaturated atom. Here if we see, of these two nitrogens, this one is saturated nitrogen, hence the numbering will start from this nitrogen, and this compound can be called as 1,3-diaza, and the next is the ring size. Okay. Here we will move in a systematic and a sequential manner. If more than one type of heteroatom is present, here we saw two heteroatoms of the same type is addressed. Now, if more than one type of heteroatom is present in the ring, then the name will include more than one prefix with their location in order to indicate the relative position of the heteroatom. Okay. The atom prefixes have a strict order of priority or preference in which they are to be listed. For example, oxa is used for oxygen. It always comes before aza. We can come across terms like oxaza. Okay. However, should be omitted. That is, this A is omitted when the two terms are combined. Hence, we call it as oxaza. The heteroatom of the higher or highest priority. Here we can see two heteroatoms are there, sulfur and nitrogen, where sulfur has got higher priority as compared to nitrogen. Hence, numbering will start from sulfur and it will move like this so that nitrogen also gets the minimum possible number. Okay. This compound is a thiaza derivative. Okay. Here, when we do the numbering is done in such a way that the smallest, the higher priority bearing heteroatom gets first position and the next heteroatom gets the minimum possible number. For example, here if we see this structure, the structure can be called as 1,3-thiaza derivative, which has got 1 methyl substitution at position number 4. Now, while doing the nomenclature, we have to choose the appropriate suffix from the table number 2, depending on whether or not nitrogen is present in the ring. In addition, what is the size of the ring, whether there is any sort of saturation, unsaturation, or what sort of degree of saturation is associated with the ring, that also comes in the suffix part. So, till now we have learned when we go for IUPAC nomenclature, first position is the locants, that is position number of the heteroatoms, followed by the prefix. What prefix? Prefix of the heteroatom. Okay, and how they are attached? They are attached as per their location is decided based on their priority. Atom having higher priority is given first priority, and that having lesser priority is given a comparatively number which gives minimum possible number to the atom in the ring. Here we can see the example. At the last, we have to combine the prefix and suffix together, and we have to drop the first vowel if two vowels they come together, as we saw in case of oxa and aza. Two A come together, so we omit the A associated with oxa. When two vowels they come together, then the first vowel we have to drop it. Okay. Here is the table number 2. If we have got a tricyclic structure with nitrogen present and the ring is unsaturated one, the suffix will be irine. If at all it is saturated, we will call it as iridine. Here we are seeing the suffix for 4-membered rings, unsaturated, ETE, whereas saturated one are associated with suffix etidine. Likewise, 5-membered heterocyclic ring, which is unsaturated, is called OLE, or it is given a suffix OLE, whereas here, if at all it is saturated one, then we will call it as olidine. Likewise, a suffix for all the types of or all sorts of rings with all sorts of heteroatom is given here. Here, special emphasis is given on the presence or absence of nitrogen. For example, if at all we get a structure like this, it is a tricyclic compound. Okay, it is saturated one. Tricyclic compound with saturation is denoted, is given the suffix iridine. Here the prefix is aza. Why? Because this ring contains nitrogen atom as heteroatom. Hence, the prefix for this heterocycle is aza. As it is a three-membered and fully saturated ring, the suffix is iridine. Okay. Now, when we combine this prefix and suffix, we can see aza-iridine. Aza-iridine. Two vowels, they come together. So, first one will be dropped. And we will get at the end a name as aziridine. So, this is representing a structure called aziridine. Now, when we talk about, this is a four-membered ring. Okay, when a four-membered ring is associated with two heteroatoms, oxygen and nitrogen. Here, oxygen has higher priority than nitrogen, hence the numbering should start with oxygen. So here we have to give the position number to both the heteroatoms. It is shown here as 1, 2. This represents the locants. This is followed by prefix. Prefix is oxa and aza. Both are combined. The first vowel will be dropped. Oxaza. Hence 1, 2, oxaza. Likewise, it is a saturated ring as per table number 2. Here we can see four-membered ring, saturated, 18. Four-membered and fully saturated ring is given suffix etidine. So by combining the prefix and suffix, here we can see, here we got oxaza. That oxaza is combined with etidine. Here we can see there are two vowels coming back to back. So the first one will be dropped. A is dropped here and we will get the correct name as 1, 2, oxazetidine. Clear? Now see the next, let's see the next example. Here there are three heteroatoms, of which one is oxygen and two are nitrogens. So first thing that we have to do here is the numbering of the ring. Here, as the ring bears heteroatom oxygen as well as two nitrogen, so prefix will be oxa, and for two nitrogen, the prefix to be used is diaza. Next, we have to give the position number or numbering of the ring. Numbering as per the priority list should start with oxygen as position number 1. And we have to move like this. So position number 2 and 5 is given to the two nitrogen atoms or aza atoms, whereas position number 1 is occupied by oxa. So we will call it as 1, 2, 5 oxa diaza. 1, 2, 5 oxa diaza. Here 1 is representing the position of oxa, 2 and 5 it is giving the indication about the position of two nitrogen atoms. Okay, here when we combine oxa with diaza, we get oxadiaza. Okay, when we combine oxa with diaza, here two vowels, they do not come together. Okay, hence A of oxa is not dropped here. Only when two vowels, they come back to back or come adjacent to each other, then the vowel attached to the first prefix is dropped. Here, there is no question of two vowels, hence everything is written as it is. Now, as because now it comes, now locant is clear, prefix is done. We have to attach the suffix. Now, when we talk about unsaturated ring, to be specific, 5-membered fully unsaturated ring, it is associated with a suffix OLE. Here we can see 5-membered ring, unsaturated ring is supposed to have a suffix OLE. So when suffix and prefix both are attached or combined, we get the final name of the structure 1,2,5 oxadiazole. Here, aza and OLE come together, A is dropped, hence oxadiazole. Here we can see a 6-membered saturated ring with only one nitrogen atom. 6-membered ring with one nitrogen atom present its heteroatom. At the same time, this nitrogen is saturated one. So the prefix perhydro is followed by the name of fully unsaturated 6-membered ring with one nitrogen. The name is azine. Okay, when we talk about a 6-membered ring with nitrogen, it is called azine. However, as because it is a saturated one, so we have to attach the prefix perhydro. Hence, the full name is perhydroazine. Here I have taken some of the structure and I wish you to do its nomenclature based on the hints or based on the rules that we have followed till now. The partial unsaturation in heterocyclic compounds can be indicated by one of the following methods. First is the position of nitrogen or carbon atom which bear the extra hydrogen atom. And it must be indicated by numbers and italic capital H. For example, if at some position one hydrogen is attached, then the position number, then the one attachment of or presence of one hydrogen is denoted like this. If two hydrogen are attached, then we will write it like this. And this should be followed by the name of maximally unsaturated ring. For example, when we talk about a partially unsaturated ring like this, here one bond is saturated and here it is unsaturated. So the ring structure is called as a partially unsaturated heterocyclic ring. Here we can see this position number 2 and position number 3. They are associated with one hydrogen atom each. Hence 2H, 3H, oxole. Oxole is the name of the maximum unsaturated ring. However, unsaturated ring is taken and its position number 2 and 3 is saturated. Hence, 2H, 3H oxole. Here, if we see the structure, only this position number 1 is saturated. Here, 1H, the unsaturated ring is called as 7-membered. Unsaturated ring is denoted as azapine. Here we can see position number 5 is saturated, hence 5H, 1, 2, 3, oxathiazole. Likewise, here we can see the structure, or we can denote this structure as 4H because the fourth position is saturated here, hence 4H oxane. Next thing that we have to take care is the words dihydro, trihydro, or tetrahydro. They are used if 2 or 3 or 4 atoms are saturated. These words are preceded by the numbers to indicate the position of the saturated atoms. And they should be numbered in such a way that they get as low as possible number. And this should be followed by the corresponding fully unsaturated Hans Widman name. For example, here we can see it is representing 6-membered heterocyclic ring with nitrogen as heteroatom present. Here we can see 1 and 2 position is saturated. Hence we will call it as 1,2-dihydroazine. Okay, instead of denoting it as 1H, 2H dash dihydroazine, we can call it as 1,2-dihydroazine. Here we can see position number 1 and 4 is saturated, hence 1 and 4, 1, 4 dash dihydroazine. Here we can see position number 2, 3, 4, 5. All are saturated. Hence the name 2, 3, 4, 5 dash tetrahydroazine. Here it is 2, 3 position is saturated. Hence 2, 3 dihydro because they are representing 2 positions and both the positions are associated with 1 hydrogen each. Hence 2, 3 dihydroxole. The third point is when the partially unsaturated 4 and 5-member rings contain one double bond, they are given special Hans Widman suffix as per this table number 3. As per this, the double bond is specified as delta 1, delta 2, delta 3, etc., which indicates 1 and 2 and 3, 3 and 4. If it is, or if the double bond is placed between 1 and 2, 2 and 3, or 3 and 4 respectively. That is, if the double bond is present between as delta 3. Okay. Here are a few examples. Next, we will see the nomenclature of fused ring system. When we talk about the nomenclature, or to be specific, Hans-Widman method or IPAC method of nomenclature of fused ring system, first we have to remember that what is fused ring, or what is the meaning of fusion? When in a structure there is fusion of two rings, we call it as fused ring structure. Okay. It may be a fusion of 2 rings, 3 rings, or more than that. It depends. However, fusion is a term which is used to describe the process of joining two separate rings with the maximum number of non-cumulative double bonds via 2 atoms and 1 common bond. Here we can see 2 rings are fused with and when they are fused in such a way that there is no question of 2 cumulative double bonds, and when this fusion takes place we can see there is involvement of 2 atoms and there occurs 1 bond in common for both the rings. These fused rings may be orthofused or they may be ortho and perifused ring. What is the meaning of orthofused ring? Orthofused rings are those rings that have only 2 common atoms and 1 bond in common, as we can see here, as is the case of naphthalene. Okay. Now, when we talk about ortho and perifused rings, it includes rings which are found in a polycyclic compound, and the rings are fused in such a way that the ortho fused ring is attached or it is fused to some other rings in turn, or else we can say it includes polycyclic compound with a ring that is orthofused to different sides of 2 other rings. Okay, which are themselves orthofused. For simplification, here we can see the structure. It is structure of phenylene. Here we can see it is the structure of 1H phenylene, which is considered as ortho-perifused compound. Here, this phenylene is considered as being composed of 3 benzene rings. Each is ortho-perifused. That means this one is attached to these 2 orthofused. This is attached to these 2. And this is attached to this 2. Orthofusion. These 2 have got orthofusion in relation to each other. However, when this orthofused ring, we will call it as ortho-perifused ring. Such type of rings are in general found in polycyclic compounds, and polycyclic compounds incorporating one heterocyclic ring or fused heterocyclic ring, heterocyclic system is fused to benzene, then we will get an orthoperifused structure called as benzoheterocycle. Also, bicyclic compounds with two fused heterocyclic rings are also quite well known. Both the types can be named according to certain rules. Now let us see the nomenclature of benzo-fused compounds. Unless it is listed as a trivially named heterobicycle, a benzene ring is fused to a heteromonocycle of 5 or more members, or a heterocyclic is named by prefixing the word benzo to a letter indicating the position of fusion, and that position of fusion is always shown in square brackets followed by the name of the heterocyclic ring. For example, if at all we talk about a benzo-fused ring, then the nomenclature should bear a structure like this. First benzo, then the square bracket, which gives us the position of fusion, followed by the name of the heterocyclic ring. Benzene ring is fused with heterocyclic ring. The position at which they are fused is shown here within this square bracket. Clear? Now, for designating the position of fusion, the peripheral bonds of the heterocyclic ring are consecutively assigned alphabetical letters, starting with 1,2 bond as A side. Here, read it as 1,2 bond, that is bond between position number 1 and 2 is denoted as A side, and the labeling is continued around the ring to give the common bond the lowest order. Here we can see these rules followed in a clear way. Here we can see benzene ring is fused with furan. Okay, and where they are fused along the B surface of furan. Here benzene is fused with furan. Okay, the heteroatom pairing structure or ring is furan here. So this bond between 1 and 2 is given or denoted as side A, 2, 3, B, then C, then D and E. I'm talking about the name of this side, or this face is denoted as A, this one as B, this one as C, this one as D, and this one is denoted as E. Here the two rings are fused along the B face, hence the name benzo B-furan. Here we can see benzene ring is fused with thiophene. Thigh, 7-membered epene, benzothiophene. Where it is fused, the site of fusion is 1, 2, or face between 1 and position number 2 is denoted as A, next is B, next is C, next is D. Hence the name benzo D-thiophene. Similarly, we can see the nomenclature in the rest of the structures. Here it is benzo B-pyrrole. It is also denoted as indole. Here we can see benzopyridine. It is also known as quinoline. When we denote it as a benzo-fused ring, then we call it as benzo B-pyridine. B here represents the surface along which the two rings are fused. Okay. Here also we can see the structure of benzo F quinoline. Here you can see the site of fusion is A, B, C, D, E, and F. Hence it is fused, the two rings are fused along the surface F. Benzo F quinoline. Here we can see the quinoline ring is fused with the benzene ring. Hence we call it as benzo F quinoline. To the F surface of quinoline, benzene ring is fused. Here we can see benzo C thiophene. Next, let us see the nomenclature of fused heterocyclic compounds. Naming a fused heterocyclic system composed of two monoheterocyclic units or benzoheterocycles, that is chromine, fused with another heterocyclic ring, is based upon considering one system as the parent or the base and the second is considered as the substituent. So in a simple statement or in a simpler way, we can say when we talk about fused heterocyclic system where there are two monoheterocyclic units or benzoheterocyclic, in that case, one is considered as the base or the parent and the second is considered as a substituent on it. Here, the name is formed of first the name of the minor ring, then the number, comma, number letter, followed by name of the major ring. One heterocycle is attached to second heterocycle. Okay, they are not fused, they are attached. Okay. The minor ring is taken first, then the site of fusion, then the number at which they are fused or attached, then the site of fusion, that is surface A, B, C, D, E, F, etc., followed by the name of the major ring. Okay, here we can see the various prefix which are given to the substituent rings. Now let us see the nomenclature of some fused heterocycles. Here the numbers, now when we talk about, here we can see name of the minor ring followed by number, then number letter, and followed by the name of the major ring. Here we can see two heterocyclic rings, they are attached, okay, or they are fused with each other. Then one is taken as the base and second is taken as the substituent on it. The substituent is considered as minor ring and the base is considered as the major ring. And both are separated by a square bracket containing the number and the number letter. The numbers here indicate which atom in the minor ring are common to the major ring. As we have already said, one ring is considered as the major ring and the second is considered as the minor ring. Within the bracket, we saw number as well as number letter. What that number indicates? The number indicates which atom in the minor ring are common to the major ring or the site of fusion in the minor ring. The order of the numbers indicate which atom of the minor ring is encountered closest to atom 1 in the major numbering system. Okay, here it is observed that these numbers may be written in ascending or descending order. It does not matter. Next is the letter number. What is this letter number? Here The letter defines the position of attachment of the minor ring to the major ring. That is the site of fusion, the fusion site in the base component. Finally, a suffix is added which indicates the name of the base ring. Okay. The numbering system for the whole fused system is not the same as the numbers in the square brackets. Here, notice that the numbering system for the whole fused system, suppose A is one fused ring system and B is one fused ring system and they are attached to each other. Then after being fused, the whole fused ring system is numbered in a totally different manner. Okay, and the numbering system for the whole fused system is not same as the numbers in the square brackets. That is, there are three numbering systems, one of the minor ring, one of the major ring, and the third is the system as a whole. The entire fused system is numbered as a whole. How it is done, as we will see the examples, that time these concepts will be very, very clear. So don't worry for the time being. Just try to understand the thing. That's all. Now, priority order of component ring system. When we talk about priority order of component ring system, selection of parent component or attached component, which one will become the parent and which one will become, which part of the fused ring system will become the component or attachment, how that is determined. The selection of parent component or attached component is based on the following rules. Rule number 1, a heterocyclic ring containing the heteroatom occurring earliest in the order nitrogen, followed by fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, etc. That is, ring containing nitrogen is preferred to the ring which does not contain nitrogen. Okay, or we can say the ring containing nitrogen is preferred to the rings that does not contain nitrogen or they contain oxygen or sulfur. Now here we can see the example. Okay, here we can see there are 3 rings and they are fused with each other. Here let us assume this is the site of fusion between this ring and this ring. So here, if we see priority wise, nitrogen is present in this ring, whereas here there is no question of nitrogen. So this will become the parent ring and this will become the attachment. Okay, here you can see both the rings are separated to clearly show you the substituent ring and the base or parent ring. Here the parent ring is pyrrole and the surface of fusion is surface P and surface C between number 3 and 4. Okay, now when this chromeno ring is fused with this structure, we get a structure like this. And how we will do this nomenclature of this fused ring? We will name it as chromeno 2, 3. That is the surface 2 and 3 of the substituent is fused to the surface C. That is chromeno's number 2 and 3 position is fused with the C surface of this pyrrole. Hence, chromeno 2,3-C pyrrole. This pyrrole's C phase is fused with the or fused along the 2,3 or the bond between position number 2 and 3 of chromeno ring. Hence the name chromeno within square bracket 2,3-C pyrrole. Clear? Now let us see another example. Here also we can see there are two rings fused. Which one will become the parent chain and which one will become the substituent chain? Now if we remember the priorities list, here we can see nitrogen is given higher priority as compared to oxygen and sulfur. So in this ring structure, here you observe oxygen has got higher priority as compared to sulfur. So here in this fused ring structure, this oxygen bearing ring will become the parent ring and the sulfur bearing ring is considered as substituent ring because O is preferred over sulfur in the priority list. Okay, the O ring is furan ring, whereas this ring is called thiopyrano ring. Okay, this thiopyrano ring is associated with one site of saturation. Here we can see it is saturated. Okay. Now when we do the numbering, it is numbered like 1, 2, 3, 4, 5, 6. Okay. The site of fusion, along which site it is fused along this site. That is along 2, 3 or 3, 2. Here we can see this thiopyrano ring. Thiopyrano and furan both are separated by a square bracket along which surface of the substituent is attached the surface 3, 2 or 2, 3. Followed by along which surface of this furan ring this fusion has taken place, along surface B. Hence 3, 2-B is placed within the square bracket. Now when we see the entire fused ring system, then as we have already discussed, numbering of this parent ring is different, numbering of this substituent ring is different, and the numbering of the entire fused system in whole is different. Now if we see the numbering of this entire fused structure, we will start the numbering with the heteroatom having higher priority, that is oxygen, and we will move the numbering like 1, 2, 3, next 4. Remember, when there is a fused site or the site of fusion is there and the site of fusion bears carbon atom, that time no number is given here. Okay, so the position number 3 is followed by the next pre-site where there is no common fused surface. So this is position number 4, 5, 6 and 7. Here we can observe the site of saturation has been changed to position number 7. Hence the saturated site is denoted by 7H-thiopyrano 3,2-B furan. Next, let us see rule number 2. A heterocyclic component containing the largest possible individual ring. Here we can see 2 rings are fused. Numbering of the whole system should start from O, that is oxygen in the furan ring. In order to give the two heteroatoms, here numbering of the whole system is supposed to start in such a way that the oxygen in the furan ring is given position number 1, and here we get and one more thing here I must say is, when we do the numbering of the whole system, the numbering should start from oxygen, and it should be done in such a way that both the heteroatoms, they get minimum possible location or minimum possible position number. Here either they may get position number 14, 15. However, the heteroatom locant 14 starting from O in the pyrene ring gives them locant 15. Thus, it is indicated the H takes locant number 2. See, if we talk about the entire ring system, then if we do the numbering 1, 2, 3, 4, 1 4 position. Now, if we do the numbering like this, or if we start the numbering from this, then 1, 2, 3, 4, 5. Here, we should do the numbering in such a way that the minimum possible number is acquired by both the heteroatoms. Rule number 3. A heterocyclic component containing the greater number of heteroatoms of any kind. Here we can see the example. Here we can see both the rings bear heteroatom. However, here the number of heteroatoms is more as compared to this. Okay, here we have to note that the whole molecule is numbered starting from pyridine ring in order to give the 3 heteroatoms the lowest possible number. Okay, here when we start the numbering, here what we have to remember, see, when we see a structure like this becomes the parent chain and this becomes the substituent. So the surface along which they are fused is D surface of the parent chain. Here we can see it is oxazine. Okay, and the surface along which the substituent is attached is position number 2, 3. This hence 2, 3 dash D is placed within the square bracket. Here pyrido ring is fused with oxazine. Okay, and when we see the numbering of the whole fused ring, we have to remember that numbering should be done in such a way that minimum possible number is given to the heteroatoms. Okay, if we start the numbering from this right hand top corner of the fused ring, then we will move like this and we get a position 1, 6, 7. However, if we start from the oxazine ring, this ring, then we may get number like, if we start from, see, either we have to start the numbering from this end or from the right hand top, or here if at all we are starting, then we have to start from this position. Then what will be the relative position of these 3 heteroatoms? If we start the numbering from this position, then 1, 2, 3, 4, 5. This is 2, 3, 5 position. Or else, if we start the numbering from this top end, we will get numbering like 1, 2, 3, 4, 5, 6, 7, 8. The number 238. Where we can see minimum possible number for the 3 heteroatoms. Here we can see the minimum possible number is given to the 3 heteroatoms if we do the numbering like this. Hence, this is the most correct method of numbering of this entire fused ring structure. Next is rule number 4. A heterocyclic compound or component containing the greater variety of heteroatoms. When we see a structure like this, here also heteroatoms are there, here also heteroatoms are there. Here we can see a larger variety is present, that is oxygen and nitrogen is present, whereas in this system only 2 nitrogen atoms are present as heteroatoms in the heterocyclic ring. So this ring will become the parent chain and this will become the substituent. The parent chain or the parent cycle heterocycle is fused with the substituent heterocycle along its D surface. Hence, pyrazole, oxazole, both are fused. The oxazole's D surface is fused with the pyrazole ring along the surface 3,4 or 4,3. Okay. Here we can see, for better convenience, we should number it as 4,3, which is more accurate. Okay, because here we can see the numbering sequence also. Okay, now if we move from this side, then the D surface is fused with the 4,3 side. Hence, we take the number as 4,3-D. In addition, this entire fused ring, now when it is numbered, it should be numbered in such a way that all the heteroatoms, they get minimum possible position number. Here, the numbering will start from this right hand top corner, and this nitrogen is saturated, hence the name 1H-pyrazole 4,3-D oxazole. Now, when we do this numbering, if we number it in various other ways, then we will get locations. If we start the numbering from this position, then we will get numbers like 1, 2, 3, 4, 5, 6. That is 1, 2, 4, 6 position for the 4 heteroatoms. However, if we start the numbering from the oxazole ring, then we will get numbers like 1, 3, here it is 4, 5, 6. 1, 3, 5, 6, or we will get number like, if we start from this end, 1, 2, 3, 4, 5. That is 1, 3, 4, 5. Either this or this. However, this is the minimum, or this in all, or the summation of this is lesser. Hence, this one is considered as the correct method of numbering of this entire fused ring. Rule number 5 says a heterocyclic component containing the greater number of heteroatoms is preferred most when considered in the order of fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, etc. Rule number 6 says a heterocyclic component with the lower locants for the heteroatoms is given priority. Here it is explained with the help of this structure. Rule number 7 says if a position of fusion is occupied by a heteroatom, here remember, here this site of fusion till now the examples that we saw, we observed that the site of fusion all the times they contain carbon. However, here we can see the site of fusion is bearing a heteroatom. Okay, then the name of the component rings to be used are so chosen as both to contain the heteroatom. That means the numbering or the nomenclature is done as this ring is also containing this nitrogen and this ring is also containing the nitrogen. Here we can see it is 1,3 relative position, hence it is imidazole ring. And here it is 5-member thia and aza bearing 5-member ring, hence thiazole. Where they are fused along, as because here see there is sulfur. So it sulfur and nitrogen is present in this ring. So this ring will be considered as the parent ring and this will be considered as the substituent ring. Okay. Parent, substituent, and both are fused and the position of fusion is shown within this square bracket. Here we can see the site of fusion is between position number 2 and 1. Hence 2, 1 dash B. That is the parent surface or the parent ring is fused with substituent along its surface B. Hence 2, 1 dash B thiazole. It is imidazole thiazole. The order of preference between alternative numbering system of the whole molecule. Here we can see some examples. When numbering of the whole fused ring system is done, it should start from the first atom after fusion in any direction to fulfill the following condition. First, means when there is 2 fused rings, then the first atom from the site of fusion, either numbering will start from this, or if we consider this as the site of fusion, either the numbering will start from this or from this or from this position. Any one position is correct. However, the numbering should be done in such a way that the heteroatom should get as low possible number as possible, and whichever method gives it the most or lowermost position to all the heteroatoms is considered as the correct method of numbering. See here, we can see various methods of numbering. Here the numbering, we are starting from the right hand top corner. Here right hand bottom corner, we are starting the numbering. Here if we see left hand bottom, from the left hand bottom we are starting the numbering, because always this numbering should start from any of the first site after the site of fusion. Okay, here if we compare all the 3 methods of numbering, then we can see that the numbering where position 1, 3, 4 is given to this to the 3 heteroatoms is preferred over 136 or 146, because here the 3 heteroatoms, they occupy comparatively lower possible number as compared to these 2 methods of numbering. Clear? So this one is the correct method of numbering. Second thing we have to take care is give low numbers for heteroatoms of higher priority. If oxygen and sulfur both are present, numbering may start from this or this. However, while doing the numbering, we have to first take care that both the heteroatoms get the minimum possible number, and at the same time we also have to take care that lower number should be given to the heteroatom with higher priority. Okay, here if we see oxygen has got higher priority as compared to sulfur, hence the numbering should start with oxygen so that oxygen gets lower number as compared to sulfur. If we start it from this way, then oxygen will get very high number, which is wrong. As per this direction, what we have to do? We have to give minimum possible number or minimum possible position to the heteroatom with higher priority. The next thing that we have to take care is give low numbers to fusion carbon atoms. Here we can see the same fused ring structure is numbered in several ways. Here if we see the numbering starts with the right hand top corner, and the numbering is done like 1, 2, 3, 4. Here the site of fusion bears 4A. Next 5, 6, 7, and if at all the site of fusion bears any other atom other than carbon, then we have to give it a number. So 1 to 8 as the number. Now if we start the numbering from this point, then we get numbering like this. If we start the numbering from this end, then we get numbering like this: 1, 2, 3, 4, 5, 6, 7, 8. Now, which one is the correct one? Here, if we see the numbering, here we can see where all the 4 heteroatoms, they get minimum possible number. This one will give the most correct method of numbering. Next thing that we have to take care is, while doing the numbering of fused ring system, we have to take care that we should give lower numbers to indicate hydrogen atoms. Here, see, in this fused ring system, this site is saturated and this site is saturated. Okay, here the numbering should be done in such a way that the saturated sites should get as low number as possible. Here we can see, if we see the numbering from this side, then we can say the saturated site gets the position 2 and 4. However, if at all we start the numbering from this, then we get the saturated sites as number 2 and 6, which is higher. So this method of numbering is correct or preferred. So we have discussed various rules for doing the IUPAC nomenclature of various heterocyclic rings, fused heterocyclic rings, etc. Based on this, I would like you to try to name these following compounds. In the next class, I will ask you the name of these compounds. Okay. You just try to find out the name of this compound based on the rules that we have studied till now. So, as a conclusion, what we can say is, the schemes for deriving the base component of a fused ring system says the following questions should be asked. Number 1, is there only one ring which contains nitrogen? If yes, choose this as the base component. Okay. If there are two rings and they have the same heteroatoms, but their size is different, then the larger one should be preferred as the parent chain. When two rings of the same size but having different atoms are there, then choose the ring containing heteroatom of highest priority as the parent chain. Are the rings of the same size but contain different number of heteroatoms? Then choose the ring with a greater number. When there are two rings of the same size and same number of different heteroatoms, what I said, two rings of same size and same number of different heteroatoms, then the ring with the greatest variety of heteroatoms is chosen as the parent ring. Are the two rings have the same size and the same number and type of heteroatoms? Then we have to choose the ring with the lower numbers for heteroatoms. So this is the summary of the nomenclature rules. With this, we come to an end to the nomenclature or various methods of nomenclature for heterocyclic compounds.